Yeah, so thanks everyone, and also thanks for the conference to invite me to give this talk. So my name is Jasper. I've been doing security work for about 20 or so years now professionally. Seen lots of different things from software to hardware. For the last, since about 2006-07, I've been working with Riscure, where we focus a lot on embedded security. And in that space, we see a lot of secure boot ROMs. Specifically, we see the code and we see everything that goes wrong there. Now, just like Olivier, I have a stack of NDAs on my desk. So I'm going to take the things that we see, but I'm giving you the public examples of where you can look up where other people have found things and publish these things. So I'll first go a little bit, but I won't bore you too long with it, but go a little bit on the theory behind secure boot and what does it do and what should it do. And then I'll go into sort of the top 10 things that we've seen. So the idea behind secure boot is that we try to make sure that all the code that's running on a platform has actually been signed and authenticated. In other words, a manufacturer is trying to make sure that it's just their code that's running on the platform. And the way that this is done is we start with an internal boot ROM, and we've seen from Chris's roughly what that means in silicon. But the internal boot ROM will have a part of the program there does a digital signature verification over some usually flash image that's going to boot next. That will do other initialization and then check the signature for the next stage. And so it goes all the way down to like an operating system and sometimes even applications. And when you're going through this chain, the privileges that code has on the platform usually go down. So one of the tasks of each of these phases is also to further lock down and further configure the device until it sort of ends up in the end state where the applications are safely sandboxed. Yeah, so some common steps that you see here is there's always some sort of internal boot ROM. If you're talking about mobile phones, for instance, typically in the first stages you'll have the trusted execution environment being set up. Then later comes Linux and applications, for instance, in the Android space. But besides secure boot, a lot of other things happen during platform initialization. So we are doing things like locking down memory. So configuring in an MPU or in an MMU which ranges can be used for code, data, what peripherals can access what parts, etc. So usually when a platform comes up in the initial state, everything can access everything. So it needs to be locked down. So that's one of the things that's happening. Another thing is that there's usually a lot of configuration data. So these ROMs, they're not unique for one product. They make one ROM and it's used in a lot of different products. So the ROM will read out these OTP, these one-time programmable bits, and it will do things depending on that OTP. So in other cases, there might also be like embedded files that have a configuration, and it will act according to that. ROMs are also used typically in manufacturing. So imagine you're manufacturing a device. Once the silicon wafer is made, you have the ROM in there, but you have nothing in your flash or in your EEPROM or even in your fuses. So that all needs to be initialized during manufacturing. So within ROM, there's usually different modes that are only used during manufacturing to initialize all these bits. So for instance, it will download a firmware that comes from the manufacturing line, which will program the final firmware, program the OTP, etc. Then there's a bunch of debugging facilities somewhere in the boot chain. So that in the field you can debug what's going on. Like my device crashed, you send it back to the manufacturer. They want to know what's up. And also for in-field servicing, sometimes for firmware upgrades. Then, besides that, there's also different power modes. So when you cold boot your laptop, but then later on you close it and it falls asleep, you open it back up, it goes through a different execution path, that ROM. So it's actually trying to speed up that execution. So a lot of sort of shortcuts need to be taken, and if those shortcuts are badly implemented, you might affect security as well. So these boot codes, they have to support many different use cases. They're constrained in power and time. It's actually quite an engineering challenge to get it right. So that's sort of the prelude to why these things go wrong. So let me now take 10 different themes that we've seen over the years and explain them to you. So this is actually the chain of trust in an Android boot platform. And what you see here is something called the PBL, the primary bootloader, which is ROM code, that then checks the second stage, which is the secondary bootloader, which checks Android boot, which checks the trust zone kernel and the resource power manager and the power management IC. All these different things get checked. But in this case, what went wrong is that somehow, for some reason, and they never figured out exactly why, but the SBL was signed, but that signature was just never checked. So you could replace the SBL and just boot your own code here. So this is a theme that we see. So we call it verification mistakes. So if something is not signed, what is it actually used for? And you start seeing problems, for instance, when there are firmwares that might be signed, but for instance, they forgot to sign the header, like the load address or something is wrong, or the size is wrong. At that point, you might be able to get into the system just by manipulating those fields. So the failure is really to start interpreting information that you get that's attacker controlled before you've properly verified it. So there's a bunch of examples, and I'll publish the slides later. I guess they'll end up on the website for hardwear.io. I'm not sure. I hear a yes somewhere. Yes. So you can click on these links and read up on all of these examples. But really, just sign everything that you can, if you can. And don't use any data before you've actually checked it. And that specifically goes into headers and addresses and pointers and things of that nature. Now, I know that you can't always sign everything, but if you're looking at pointers and addresses, just make sure they fall within exactly the ranges that you have in your destination buffer. Just these kind of checks to make sure that you're not overriding anything. So that was number 10. On to number 9. So this is a nice example. I don't think Kate is in the audience today, but yeah, I know she was here yesterday. So she may have shown you a lot more detail about this than I have. But the problem here is that there's actually a firmware upgrade path on the Nintendo that goes through USB. And what it does at some point, there's a buffer overflow. So an attacker can actually overwrite a bunch of data on the in memory, but not necessarily in stack. And then the second vulnerability actually is a mem copy that copies all of that attacker control data right into the DMA buffer, but also overrides the attacker stack. So that's instant code execution. So there's obviously many problems here, but well, I've taken this example to show that the firmware update mechanisms themselves also need to be protected. So not just the image itself needs to be signed, but you also have to make sure that the mechanism around eating such an image and then burning it on the system, that also needs to be looked at. Now, I'm not arguing against firmware upgrade mechanisms at all, because I think they're very important. You need it in order to be able to fix bugs while you're in the field. But you really must harden the mechanism itself. And things where we see difficult regularly is that often these firmware images, they don't always fit into the memory at boot time or into like a little SRAM that they're using. So what you get is that these images get chunked, and chunks get individually verified for like their HMAC or something like that. But you need to make sure that you stitch all these chunks together properly in the final binary as well. Because if you can like rearrange blocks, or you can write them in places where it's not expected, you can also use that to basically hack yourself in. Sometimes what we also see is that the updated firmware, so the image that you're actually going to burn, you should do the same kind of security checks as you would do on a boot. Just make sure you just duplicate all those things and you do the same thing. Should we do questions at the end? Okay, thanks. So, well, the mitigation here is really limit the functionality to just purely the flash image burning if you can. So things like partial upgrades, individual blocks. I know that sometimes you have engineering limitations, but really try to keep it as simple as you can. Because the more you expose to an attacker in terms of functionality, the more that there could potentially go wrong. And always see if your platform supports it, use anti-rollback. So anti-rollback is a feature where in your firmware, you put a version number, like a security version number, and every time during boot, the platform sees that security number and it's higher than the last time it's booted, it will actually update some fuses. And by updating those fuses, it makes sure that you can check whether a previous version has been booted and then just deny boot. So you make sure that the version can only go up and never down. So this prevents downgrade attacks where an attacker would put a vulnerable version back in place. This is a fun one too. So actually, a lot of the times, big parts of boot code is actually drivers and parsers. And these things are notoriously complex. So if you have a recovery mechanism that goes through USB or SD cards or MMC or you name it, that means you have to implement a driver for that in the boot code. And these drivers are not trivial drivers. Like there's quite a bit of code involved. And by definition, they're taking data from the outside world and have to do something with it. So this is sort of the area where we see a lot of bugs. They're necessary because you want to be able to boot your system in case there's a failure. But yeah, there's a lot of potential there for just your traditional software bugs like integer overflows and buffer overflows and you name it. So again, a bunch of examples from iPhones and Nintendos. And really what you want to do here is you want to make sure that you review your code, do fuzzing. These are software vulnerabilities, so you can just do the typical software things, except that now you need to come in through a hardware interface. This is one of the more low level in the sense that it's really easy hacks I've done not personally, but that we as a company have done in the past. So imagine you have a device with a big firmware, and they oversized the firmware a bit, so the actual proper boot code was sort of sitting in the top block, and this was not used. So the signature verification went over the code that was here. So this is in principle all attacker controlled. Now, that's not necessarily useful, because as soon as this started executing, it was executing from here. But this is a bit of an older system, so it was executing code from the external flash. So this is an external flash. Now, what happens is that while it's running this code, we are controlling all the address lines. Specifically, we're controlling the address line which tells whether you should look in the upper or the lower page. That's just one bit somewhere. So we soldered a wire onto that address bus, and we put a little button on it, a physical button. So while this thing is executing and booting, if you press the button, we would actually pull that line high, and we would instead be loading code from this page. So even though this was all properly signed and verified, during execution we just popped it over. And since there's no timing required or constraints almost here, because at any point in time during the boot, this code will be, or the instruction pointer will be somewhere here. So once we pull that address line, we're somewhere here, but you just build a ginormous knob sled and your attacker code at the bottom, and you got it. So this was cool because normally we're dealing with FPGAs for all this precise timing and everything, but this one you could literally just with a button corrupt the boot. So this is a race condition or a time of check, time of use issue. Between the verification of something and the use of something, you got to make sure that an attacker cannot get in between there. And that can happen because, for instance, a flash is external, but you can also think about DMA attacks, right? So if the code that you're executing is in memory, and for some reason an attacker has been able to get DMA access, after the signature verification over the memory, he can just copy any data in there and control the system that way. So also again, there's many examples from both the PC world and the embedded world. So really, to really try to prevent any of that access, and typically this is done by first copying something to internal memory and then doing the verification. Now the more astute listeners will say, but Jasper, you said earlier, don't do anything before you verify it. Well, this is sort of an exception. So really try to copy, verify all the pointers and the sizes, make sure that it sort of doesn't override anything in your SRAM, but only then you can do a digital signature verification, because doing it on the external side just doesn't make sense because of this issue. This is one of the all-time favorites, I guess, from the gaming world. So this is a timing attack, and what's happening here is that we, or at least in the Xbox world, we want to load our own code during boot. And in this case, the boot code itself was signed with an HMAC. Now, the way an HMAC works is that it takes a symmetric key and it signs a blob of data, and then you can verify the signature verify or create that signature if you have the key. So any of the proper firmwares have been signed using this key, and the same key is in the Xbox. It can verify any image that it receives. Now, they made one big mistake. What happens is that when you provide your attacker-based image, you cannot give it the proper HMAC because you don't know the key. But the way that the verification works is that the Xbox will calculate the proper HMAC over the firmware image that you've given it, and then it will compare the signature that it has calculated to the signature that you have given it. Now, so far so good, but the comparison was done byte by byte. And as soon as they found a byte that's incorrect in the signature, they would return. So this is a classical timing attack. So you can actually, by timing how long it takes to verify this flash image, you could identify which byte in your signature was wrong. Meaning that I can just provide it with 256 signatures where I just increase the first byte every time. And for one out of those 256, the execution should take just slightly longer because that was the correct byte and it has gone to comparing the second byte. Now I know the first byte and I just rinse and repeat. So this is actually a nice example of sort of operationalizing, or I guess commercializing that attack. So you could make these boards out of it, you solder it to the system, and it does the timing and it does the brute forcing for you. And on this one, I was talking to my colleague over lunch, there's improved versions of this, but at this point it took about 2 hours to load your own firmware. So it was pretty good, pretty cool. So that's what I just talked about. Yeah, the mitigation is actually quite simple. You just use a time constant comparison. So instead of quitting after the first byte that you see, you just keep comparing each of the bytes and then you exit. Just make sure you don't put any like if conditions in that loop. Like if this byte doesn't equal that could also be a timing leak. So the trick is to actually, from the two arrays that you're comparing, you just XOR the bytes, and the result you logical OR onto a state variable. So if they're all the same, then the XOR will be all zeros, and my OR will be 0. If any of the bits are different, then the OR will be non-zero. So that's a way to sort of, in a branchless way, implement this, and that should have no timing leak. Also here, I put a link to a paper where we explain a lot of things about how to present timing attacks, but also other side channel attacks. So this is, let me start the video while I'm talking. Oh, and I'm going to turn off the sound because it's horrible. So this is a video where they're actually demonstrating a glitching device. It's inserted in a slot machine, and as you can see here, the credits are just all of a sudden rolling up. So what's going on here? So the way that these machines are built is that they have, this is an older, like unprotected one. They have a machine where they take in dollar bills, and sort of the reader for those dollar bills sends a signal to the main core of the machine, like, hey, you know, a $1 or $10 bill is inserted. Now, when you generate large electromagnetical pulses, that communication could get disturbed and may be interpreted as, oh, somebody's inserted X amount of money. So, this is it's a really visual example of glitching. So how is this relevant to boot? Well, it turns out that fault injection is actually quite an effective way to subvert execution flow. So we do a lot of fault injection in our lab, but what we're typically aiming for is conditional branches. Remember that initial picture that I showed of like I verify the boot, and then if it's correct, I jump into the next one. That's a conditional branch. So somewhere in that boot flow, the processor decides this image is correct or it's incorrect. And it does that typically with a conditional branch instruction. So if you're able to flip that decision by doing a glitch at the right time, you might be able to load code which actually didn't have a proper signature. And some people always say, like, how do you figure out where that instruction is, right? Do you do the linear code extraction that the Chris's were talking about? And no, it's actually much more black box than that. So our typical process is we'll boot the system once. We take what's called a power trace. So we actually look at the power consumption over time of the device, which shows you electrically sort of what's going on at a very high level. You just see different waveforms that correspond to different processes. Now, next we load a firmware image where we just flip one bit in a string or something somewhere. So we don't change the code, but we do make sure that the signature is invalid. We load that as well, and we also take a power trace. Now what happens is those power traces will be roughly the same all the way up to the point where on the one hand the CPU has decided to accept the firmware, or in the other trace to reject it. And they actually go into different execution paths, and you see that the traces will start differing. So that gives me sort of but it gives me a very narrow window of time where I should be glitching. So I don't need to really know like that's exactly where particular branch instruction happens, I can just take it from the power traces. One good thing to remember is that this is seldom a persistent attack. So there are mod chips type things that do fault injection, but typically these are more like stepping stone attacks. So I'll use it once in order to load my attacker firmware, and then I dump the boot ROM, and then I go find a vulnerability, and then I can exploit that later on, so I don't always have to like glitch things. So a bunch of examples. Really, you need to, there's the hardware approach here, which is building in countermeasures against faults, which is rather expensive, typically on the hardware side. There's also some things that you can do in software to mitigate these things. So there's certain programming styles, things like, instead of checking the boot code once, check it twice or check it 3 times and see if the signature still succeeds, because doing a single fault is sort of you have a probabilistic effect there. I may have a 10% or a 1% chance of bypassing it. But if I need to glitch something 3 times, it's a 1% of 1% of 1% if it's done correctly. So there's these kind of patterns that you can do to make the attacker's life hard. So I'm going to take one more step. State errors. So sometimes, especially in these like suspend resume cycles, you need to store your state somewhere. And this is done because you want to speed up the boot when you resume a platform, which means you don't want to do all the computations again. You don't want to re-verify all those images, but you somehow want to lock them into memory in such a way that an attacker cannot tamper with them. If you do this insecurely, you might be able to exploit the fact that you can change the state just before a system goes to sleep or just after it wakes up. And this is really leads sort of to maximum privilege escalation because you're there very early on at boot. So that's, there's especially in the PC world, because their sleeping and waking up is quite an elaborate process. There's been various attacks over the years. Some of the mitigations here would be to actually cryptographically sign and verify your state. So instead of just trusting that a certain memory location where you store these things hasn't been tampered with, you sign it and you verify it on boot. Or you just reanalyze all the variables. But I realize these things have a performance overhead. So that's something that's, where performance and security aren't always friends. Also here, you should consider both logical and fault injection attacks. So logical meaning I can just flip memory bits, or maybe I can load some code that flips things before you go to sleep. But also during fault injection or during sleep, you might be able to fault a certain state. Bad fed is actually a cool example also of glitching, but it's not the category that I'm alluding to here. What bad fed did was on a embedded device that was booting up, you corrupted the memory by just sending a big EM pulse. So inside the memory, you flipped a couple of bits this way, and what actually happened was that U-boot, in all of its wisdom, during the boot phase would see that the memory was corrupted, the image was corrupted, and it would fall back to a debug mode. And it falls back into a debug mode where you have commands like this, memory write. So you basically had, during boot, arbitrary control over this system. And this is not something that you would normally be able to fall into. You really have to just corrupt something that normally you logically wouldn't have access to. But this was a really nice example of falling back to an insecure mode. And this debug, U-boot is there normally to verify these kind of signatures, but at the same time it offers this type of functionality as well. you might consider, if you're using U-boot, compiling these things out in your production systems. But it's an example of things that can go wrong with debugging. So debugging is a rather large topic. You will find debugging interfaces on every device out there, just because developers need to debug their stuff. And it's usually you will find JTAG and or UARTs with debugging consoles. Sometimes something a bit more proprietary. And in automotive, what you also see a lot is that there's like these sort of service backdoor / special readers available for modifying behavior on devices. Now, one of the things that you typically see is everybody understands that backdoors are bad. But often you'll see like, we know it's bad, but in my particular situation, it's okay because of XYZ. And then, the situation changes, requirements change, and all of a sudden it does become a huge backdoor. So the examples here, you see it a lot in, like I mentioned, in car tuning, ECUs and cables, where there's some kind of magic authentication. And this isn't always like a cryptographically hard challenge response. It's usually more like a master password that's being sent in order to open something up. A lot of the more secure chips you can actually disable or log JTAG. Maybe not from the CRISPs, but you can do it from people who are not invasively attacking your chip. Although we sometimes bypass that with fault injection as well. So these log bits are somewhere on the silicon of the chip. We've done things with voltage glitching, but also with laser glitching. So you open up the package, so you see the chip, and then you just start scanning the chip. So you say unlock, and you shoot it with a laser at one position, and you say unlock again, and you shoot it at the next position, and you just scan the entire chip until the unlock succeeds. And then you've sort of hit the area where the log bits are. Definitely used in device unique debugging facilities. Because if somebody breaks one of the chips, you don't want that to translate to all of the chips. And also, if it's possible, you don't need to always build in all of the debugging functionality in your, in the production chain. You could also imagine that in that chain of trust, you hold in your manufacturing facility, hold a special debugging image, which is also signed, but that's where you put all the debugging functionality in, and you don't put it all into production. Eventually, these things tend to leak, but it mitigates it somewhat. This was also a cool attack. So this one, the 3DS, and what they had here is they had a table with a bunch of keys, and each of these keys were encrypted, so you couldn't read out the keys directly, but you could shuffle the keys. So you could arbitrarily move these keys around to different key slots. Then there were also a bunch of firmware binaries that were signed with all their keys. So there were actually two things that you could play with an attacker. You could give it signed but encrypted images, and you could pick different ones, and you could flip around keys. And it turns out that if you have enough of these keys and you have enough of these versions, you could find a combination where the decrypted version, which you don't know, but the decrypted version actually had a jump instruction somewhere that would jump into attacker-controlled code. So this always makes me grin, these kind of things. But yeah, it's really important here to make sure that you don't allow arbitrary key combinations arbitrary keys to decrypt arbitrary data, basically. So you have to check what this key is used for. Other things that we've seen is if you sign development bootloaders with production keys. So once the development bootloader that's signed with a production key leaks out, you can use this on all the devices in the field. So that's also a problem. And then finally, make sure that you sanitize your crypto engines before you go to next boot stages. So often these things work if you have a crypto engine and it has a number of key slots. You program these slots and you say, go decrypt this part of memory or that part of memory. You want to wipe those key slots before you go into the next stages of boot. Because if somewhere down the line something gets compromised and they can still use these keys, you have a problem. So, yeah, this is really a question of reviewing this, understanding the value of all these keys, and acting accordingly, I would say. And make sure that you clear any sensitive data out of crypto engines before you proceed. Now, then the final one, number 1. How many minutes do I have? 5? I'll speak fast. And I won't go into all of the details of EDSC DSA. But you can also use crypto the wrong way. The previous one was just key material, how to use keys, but you can also use crypto the wrong way. One of the classic ones is that decryption is not the same as authentication. So I've done attacks where I had an AES CBC, and the way that AES CBC works is that I can pick a bit that I want to flip in the plain text, and that will corrupt the next block. But that might not be a problem, depending on where I am. So you always want to do a signature verification. It's different than encryption. My mother always told me to never put math on slides, but here we go. So ECDSA is a signature scheme, and it has a bunch of input parameters, but the main one to remember is that DA is the private key, M is the message, and K is the nonce. And we control M, usually as the attacker. Now, the way that this is supposed to work is that the nonce stands for number used once, that number is used once. This is just how you calculate a ECDSA signature, at least step 5 and 6. The rest is on Wikipedia. This K is the number used once, and this is the private key right here. So you don't see those as an attacker, but you do see R and S. Now, what happens if you reuse K for multiple messages, you can actually calculate the private key based on those two messages and based on the signatures of those two messages. Instantly, like this is not hard math, right? It's just basic algebra. So that's why we never reuse this. And I will repeat this one more time. A nonce is a number we only use once. So, this is what Sony did in their ECDSA code. So this is a classic in my opinion by now. So really, they in the signing algorithm for their the signing algorithm, for some reason they just used a static number. So you could just calculate the private key and create your own signatures. So now what? So I hope you understand now that securely booting a system or just booting a system is a very complex operation. There's a lot of things that go on during boot. And in the field, patching of boot components is actually really hard to impossible. So there are things like boot ROM patches, things like that. But you're not always able to also apply those. Sometimes you can only apply them during manufacturing. So 3 things that I want to leave you with. So if you're a security researcher, go learn about hardware attacks and start exploring the attack surface on these secure boots. There's a lot to see there and a lot to do, and it's a really fun exercise. For developers, nothing rocket science here. Secure development practices. Make sure that you limit the attack surface, so turn off things that you don't really need in practice, and verify that what you're doing is actually secure. And if you're an integrator, if you're selecting components, just make sure that you ask the developers or a third party to provide some assurance on what the security that's in there. The more questions they get, the more security will go to the top of mind. So with that, I guess I have how many minutes for questions? We have still 5 minutes of questions. All right, I saw, yeah. You were first, you were halfway through my talk. Oh, I don't control the mic, sorry. We'll get to you.
Sorry, Majid. So you mentioned you use simple power analysis to choose the proper timing interval for fault injection.
Yeah.
Do you also use it to target other types of attacks? For example, in your example 6, where the MAC comparison, even after that's fixed, the way you described, the XOR of two values that match will produce a very different, probably more powerful signature.
Yeah.
So if you could see that, even with constant time, you might be able to execute the same attack by monitoring power crisis. Right?
Yeah, correct. So that is a fairly big if, though, I have to say. So the secure boot example, we're talking about very high-level processes, right? Accepting or not accepting. You see a big difference. Seeing the difference in like individual bits will typically require more like differential analysis, which means that I have to take many, many traces. At that point, it might be possible, but it's kind of the next level up. Yeah.
Okay. So 2 questions. One is related to the firmware update. If you don't have a secure boot process that covers the entire kernel, which is the situation that I had,
yeah.
How do you protect that firmware upgrade module itself? Where do you put it? What do you do so that you make sure the firmware upgrade comes and you verify it, you trust that verification? That's the first question. And the second one is, as far as anti-rollback attack, how do you protect the previous version? What do you do with that information so you make sure when the next one comes, you're not rolling back?
Okay. So first question, let me first make sure that I understand your questions correctly. So in the first case, we have a firmware update mechanism, but you're unable to verify the mechanism itself digitally during boot because it's in a non-protected part. Is that correct?
Yeah, so I don't have the verification of the entire stack.
Yeah.
So if this was, I don't know, maybe user space or do I have to put it in the file system somewhere so I can make sure that software module itself.
Yeah.
What is your opinion?
So the tricky thing with chain of trust is if you break it somewhere or if you don't verify something, all bets are sort of off at that point. So I think for your firmware mechanism that's not covered in there, it's going to be hard to actually verify the mechanism itself. So you have to make sure that at least whatever that mechanism is burning into the flash gets checked upon boot again. So then at least you have coverage of what's being written. And you catch any changes at that point, but yeah, it's going to be hard to catch it during the flashing process itself. Yeah, where it writes to. Yeah. And your second question. Yeah, so the question is on the anti-rollback, how do you trust that the version is actually the correct version? So yes, you make that part of the signature. So you first signature verify that the version is correct. Then if the version is higher than what I have in my OTP, go burn OTP to the next version. And then you've sort of locked that version in. Yes. Yes, because that sort of grounds the anti-rollback version into something that's really hard to change for an attacker who isn't going invasive. Any other questions?
Hi. I'm curious about your opinion regarding the fault injection attacks that are targeting system on chips that involves DRAM decoupling from the offensive and defensive perspective. And have you ever done similar work within your company?
Are you talking about SoCs that have a DRAM integrated in the package? Yeah, so that definitely has effects on fault injection. Depending on what mechanism of fault injection we're talking to. If we're talking about VCC glitching, it shouldn't be a difference. For instance, EM glitching, you now have a layer of DRAM sort of in between DRAM is on top of your core silicon, so it's much harder to glitch. And we've seen that in practice, that it's really hard to get to the CPU. We haven't studied in depth yet if you can glitch the DRAM in such a way that it's nicely exploitable. So that would be sort of an area of research. Similar argumentation holds for laser fault injection, right? So you cannot get to the DRAM. Now, one thing that you should take in mind is that DRAM is not active from sort of the first cycle of boot. So you can get a way into boot while you have the DRAM taken off as well. So depending on your goal, you may or may not be able to achieve that goal even when you take the DRAM off in the package. It's a bit of invasive work, but you might get some steps in.
Okay.
All right.
Thank you. Thank you, Jasper.
Yeah, thank you very much.